A hypothesis test for a matched pairs study, there are two ways that we can write our hypotheses. We can write it as a single parameter mu sub d, which is the mean of the differences extended to the population, or we can make the statement as a comparison of two means, because it is valid to say that we're comparing mean estimates at Jocko's to mean estimates from other garages. We're just doing it in such a way that works with one parameter. So this first model is what we would recommend. This is best for a matched pairs study because you really only have one data set, you have one variable in your data set, there's only going to be one x bar that you're working with, and so your parameter will match your statistic in this case. So this is the best way for matched pairs, is to work with this mu sub d. This here is working with a difference of means. This is like saying mu1 minus mu2 equals 0. So this is a difference of means. And this is okay for matched pairs or for two independent samples. So both of these are valid ways of stating hypotheses in a matched pairs hypothesis test. However, we definitely need to switch over to one variable thinking if we have matched pairs. So our standard error comes directly from the standard error formula for one mean. Recall, for one mean, we had that the standard error is s over the square root of n. This is the same exact formula, but it's using s sub d as the standard deviation of the differences. And for one mean, we also had x bar minus mu naught over s over square root of n. So instead of x bar, we now have x sub d bar, or x bar sub d. Instead of mu naught, we now have 0, because our null parameter is always 0 if we're doing a matched pair study. And in place of s, we now have s sub d. It really is the same formula, just adapted to this situation. So these are the two formulas we would use for hypothesis testing, or really we would use the second one, T. So we have descriptive statistics here for the single quantitative variable, difference. And this is difference Jocko's minus other. We have a mean, a standard deviation, and an n, and these are the three things we need for a hypothesis test. So that sample size is my n, that mean is my x bar sub d, and that standard deviation is my s sub d, because all of these already apply to the column of differences. So in the example we looked at first, we used a randomization dot plot just so that we could ignore the details of what formulas might go into it and not get bogged down in that. But we're going back to a distribution theoretic approach now. So our T statistic, which is x sub d bar minus 0, we don't really have to write, over s sub d over square root of n. Looks like 115 divided by 124.833 over the square root of 10. And it can't be overstated the importance of making sure that when you enter this into your calculator, you are putting parentheses around your denominator if you do the whole thing as one statement. Otherwise, the order of operations is going to be misinterpreted. We want to make that as division in the denominator. So it's like a double division that we're doing here to calculate this. So let's bring in a calculator and do 115 divided by open parenthesis 124.833 divided by 10 square root close parenthesis and then equals to get 2.913. My hypotheses, recall, were the null hypothesis mu sub d equals 0, the alternative hypothesis mu sub d is greater than 0. So what this would look like when I put together a curve of a t-distribution, a bell-shaped curve centered at 0, and with my t-statistic as the boundary of the tail, I'm going to put it pretty far out in the tail in this case because 2.913 is getting pretty close to 3, so maybe even a little bit farther out than I've drawn it right now. We do have a right tail test because our alternative hypothesis has just a greater than, so I will just shade the right tail of this distribution. And we will now go to StatKey to find our right tail p-value. We need a t-distribution with 9 degrees of freedom. Since our sample size is 10, that tells us that we want a t-distribution with n-1 or 9 degrees of freedom. So now coming into StatKey, we will go to Theoretical Distributions T and choose 9 degrees of freedom. Right tail, and change our boundary value to the t statistic we just calculated, which is 2.913. So we get a p-value of 0.0086. A pretty small p-value, so we have very strong evidence at the very least, and based on this we can now write a conclusion. Starting with our strength of evidence, let's say that we have very strong evidence, and then think, what is it that our alternative hypothesis really states? So we have very strong evidence that the alternative hypothesis is true, and that part we definitely have to state in context. So the context here is the mean of the differences in estimates between Jocko's and other garages, and we have strong evidence that that difference is greater than 0 on average, meaning that on average Jocko's quotes are higher than quotes from other garages. We have strong evidence that on average quotes are higher at Jocko's than at other garages for similar repairs. We know in this case it was actually the same cars with the same damage that were sent to 2 garages. Now, the investigation might have been done because some fraud was suspected from Jocko's, but of course having higher estimates on average isn't automatically a sign of fraud. There could be any number of explanations, such as the garage being located in a more expensive area and therefore having more expensive rents and labor charges. We all know that, of course, some locations cost more than others, so there could be some other explanations as to why, but we do have very strong evidence that the quotes are higher on average.